his Master of Sciences degree from in statistics, and his his PhD degree in chemical engineering, both from the University of Wisconsin Madison. He is the author of 4 books, including the widely known textbook Process Dynamics, Modeling, and Control. And he has received many awards from AICHE and IFAC, and he was also elected to fellowship of the Nigerian Academy of Engineering, and also to the US National Academy of Engineering. His research areas are process control, modeling and simulation, system biology, and applied statistics. His presentation today is entitled Biological Control Systems, the Future of Engineering in Medicine. And in his presentation today, he will provide an overview of studies in which he uses a control engineering perspective for medicine, addressing the central role engineering will play in the future of medicine. So, Professor OGUNNAIKE, once again, thank you very much. I will pass the word for you.
Okay. Mauricio, well, thank you very much. And I'm really grateful to all the organizers for inviting me. I need to start by apologizing. I don't know what's going on with Google today, but I cannot share my screen with you. But my old friend, Arjimiro Seki, is going to be running the presentation from his computer. I sent it to him earlier this morning. What that means is there's going to be a little bit of, I don't know, awkwardness, because I have I have a little bit of timing issues with how I do the presentation, so just bear with us, please. And so we'll do
it's just say next, and I'll go forward.
Okay, all right. I will say next, and then. But the problem, of course, is saying next and with all the animation. But that's okay. We'll make it work. And so I'd like to start by again thanking everybody. And as Arjimiro might remember, the last time I was in Brazil was in 2016. Many of you know that I love football just as much as Brazilians love football. And the day I was leaving, the very day I was leaving Brazil to go, was the day of the final of the Olympics. And I was telling everybody that this game, Brazil was going to win. And my friends kept saying, okay, we hope your luck is going to work with us. Well, you all know what happened. By the time I finally got home, my phone was burning with messages from my friends asking me that I should be the person predicting the next games for them, because they actually won the game. So anyway, thank you very much. And I really always enjoy my visits to Brazil. Today, I'm going to be talking about some of the work that we've been doing for quite a while, and that is continuing. And so if you go to the next slide, please, where I show the outline, just scroll through everything so that everybody can see all the entire outline. Okay, so if you stop right there, I will give you an introduction. I will spend a little bit of time in the introduction, because I'm not going to assume that everybody knows something about what I'm going to talk about. But this is where I hope I can convince all of you that without control, a subject that is near and dear to all of our hearts, life as we know it will not exist. Okay, I hope I will convince you there, because I'll show you the concept of homeostasis, the concept of physiological control systems, and how, in fact, without this control, none of us will be alive. Then I would spend a little bit of time talking philosophically a bit about precision medicine. What is it? What are the principles? And then I would use some engineering perspectives to interpret what precision medicine is. Now, we've lost a little bit of time with trying to sort out the technical details and things like that to get this presentation going. So when I get to the illustrative examples, unfortunately, I wouldn't be able to spend as much time as I would love to spend. The good news is the paper has been published. and you're welcome to download the paper. And if you can't download it, let me know. I'm happy to send it to you. And then we'll summarize and conclude. So next slide, please. So the entire presentation that I'm going to give today is based on this paper. And as many of you know, for our research, and we had our 110th anniversary last year, and they asked a few of us to write some perspective papers. So this is the perspective paper I wrote. So this presentation, this entire presentation, is based on this perspective paper. I decided that rather than take something specific and go into all the details of that in this presentation, I would rather step out and zoom out and sort of show you some perspectives about where I think much of this work that we're doing is going. So next slide, please. And next. All right, so keep going, and keep going, and stop. Stop right there. Stop, please. All right, so what I want to talk about now is an experiment that actually happened in 1775. And the experiment, unfortunately, because I'm not the one driving, you can see everything before it's all done. But okay, in 1775, a professor named Charles Blagden, and you please Google him after you're done. Charles Blagden and some grad students, a dog and a beefsteak. Sounds like the beginning of a bad joke, right? One of those American bad jokes that says a rabbi, a priest, and a basketball player walked into a bar. But in this case, it's a professor of medicine, some grad students, a dog and a beefsteak, spent 45 minutes in a chamber heated up to 127 degrees Fahrenheit. Now, that's not a typo, okay? If I could see you, if I were physically in front of you, I would ask you, what do you think happened? So Ajimiro, please advance the slides. Keep going. The dogs panted, the men sweated, the grad students sweated, which grad students are still sweating till today. All of them survived, but the beefsteak cooked. The implication of that, of course, if you can go to the next point, the implication is that living organisms were able to maintain homeostasis, whereas dead organisms could not. This was the very first recorded experiment of thermoregulation, that the professor postulated the hypothesis that the only way things could have happened this way is that the thermoregulation scheme exists within living organisms. So that regardless of the temperature on the outside, which was horrifically hot, the living organism was able to maintain temperature. And from that point on, physiologists and medical people have been looking into this concept. So if you go to the next slide. Next slide, please. Just scroll through everything right there. So the objective for control, that the reason we need control is because we have to maintain physiological functions. Maintain these variables within specifications. If you go to a refinery, if you go to a chemical manufacturing plant, all of the variables of importance have specification limits. They must not be outside of that limit. It turns out the same is true for physiological systems. If you depart from those specification limits for a short period of time, you're said to be ill. Okay, so some people are unfortunately affected by COVID-19. It takes them out of the specific limits. Your viral load is outside of the specific limits, but if your immune system is working the way it's supposed to work, it will bring you back in and you will be healed. For some people, they are outside of those limits, but they stay outside of those limits permanently. You have to maintain it. These are people with high blood pressure, for example, people with diabetes. They are outside of the limits, but they can maintain it. Now, going back to people that have infected with COVID-19, in some cases, unfortunately, the viral count overwhelms the system and then death occurs. Okay? Notice that in every case that I've mentioned, there is something, the immune system, a blood pressure control system, a blood glucose control system that is struggling and working to keep you within those limits. So if you go to the next slide, please, and just the next one, yes. So this highlights, for example, what happens with blood glucose. So for normal people, you wake up in the morning, before you eat, before you drink, if you take a sample of your blood and do what's called the fasting blood glucose test, if your number is between 75 and 99, you're fine. If it's below 75, you might have hypoglycemia. If it's above 99, you might have hyperglycemia. If it's consistent, if it's very close to 150, your medical doctor will tell you that you have a problem and you have to deal with diabetes. So next slide. So if you go through, just scroll through all of them. I think that would be the best thing. So if you scroll through, yes. All right. So if you look in a physiology textbook, they will tell you that there are about 12 of these physiological systems for maintaining homeostasis. In other words, these are the systems that function within us to keep all of our physiological variables within limits. When I teach this class, and I've taught it twice now in about 15 years, I organize them into the groups you are seeing here, and I organize them as 10 instead of 12, and you'll see why from an engineering perspective. So the first group I call the master regulators. So the nervous system and the endocrine system are the master regulators. Why do I call them that? It is like if you go to a control room in a manufacturing plant. If you go to a control room in a manufacturing plant, you will see all of these monitors and things like that, where all the information comes and all the decision is being made and sent back out. Well, that's what the nervous system looks like. And the endocrine system is the one that you don't see much. That's the one that uses chemicals to do control. But the two of them combine to do some pretty fascinating things. And the nervous system, of course, the heart of the nervous system is the brain. We don't have too much time to talk about that, but we're still studying and working in understanding the brain. The next group are the group I call the defenders, protectors, and supporters. This is the immune lymphatic system. In a physiology textbook, they'll separate them. But from an engineering perspective, the two work together, and you don't really see one without the other, so I put them together. The integumentary system, that is your skin. It's like a heat transfer mode. In fact, the whole concept of control systems in physiology came about from that 1775 experiment, where they started to understand where the thermoregulation takes place and how the skin plays a significant role. The musculoskeletal system is another one where the physiology textbooks divide them into two, the muscular system and the skeletal system. For our purposes, they really go together. The other muscles, they play a part in other things like the cardiovascular system and the respiratory system. So I put them together as the musculoskeletal system. The next group is the utilities. If you go to, again, a manufacturing plant, electricity is not what you're producing. Air is not what you're producing. Water is not what you're producing. But without them, you can't do what you're doing. So the electricity, the water, the air, and all of those things are utilities that help you do what you need to do. It's exactly the same thing with the cardiovascular system, which is really a system of two pumps and pipes, your blood vessels. And all they do is circulate blood all over the place, from the heart to the periphery and back again to the heart. And what do? They bring nutrients, they exchange carbon dioxide for oxygen, they take it to the respiratory system, which is, again, the system for breathing air in and breathing air out and supplying oxygen, pretty much. The digestive system is how you bring in nutrients and you digest it and you pass it around and you extract the nutrients and then you take out the waste. The urinary system is, there's an awful lot of chemical engineering going on there, and I wish I had time to be able to talk about that, but you get a lot of separation and things like that going on in the urinary system. And finally, you get to the species propagator. And so Those of you who are below the age of 40, please enjoy it while you can, because once you pass the age of 40, the way the system works is you're vibrant and viable and things like that just before then, so you can pass on your genes to the next generation. But once you it's okay, now you can go. All right, so that's another control system, but we don't have time to go through all of that. So Ajmer, if you go to the next slide, please. All right, so this is a slide, just scroll through all of them. I'm not going to be able to spend time on this because we've already spent time, but as he's scrolling through, what I'm showing you is what all these systems contribute and what the other things they do. These systems are robust in the sense that each system is responsible for many things, and many things are carried out by different systems. So you can take a look at this. The slides are available with Ajimira and with Mauricio, and you can take a look at them a little bit later on. All right, so next slide. Let's talk about then very quickly engineering control systems and biomedical applications. I know, and I apologize for having to rush through this just because we've lost a little bit of time, but I hope I've convinced you that without these control systems, it is impossible for life to be maintained. It's impossible. So these control systems are central to maintaining physiological life. If that is the case, and I hope I've convinced you that that's the case, then it follows as a corollary that many diseases arise from control system component failures. I'm sitting in my study right now in Delaware, and I have in here a thermoregulator. It is cold outside, but I'm comfortable inside. If it starts getting too cold, I would walk over to that thermostat and take a look at it. And as an engineer, the first question I would ask is it the sensor that is not able to sense that this room is getting too cold? Or is it the controller itself that is not functioning well? Or is it the HVAC system, the heater in my basement that is not working very well? Or is it my room itself that is leaking? It doesn't matter, and you guys are control people, so you understand what I'm saying. It doesn't matter how complicated or how simple that control system is. It doesn't matter what kind of a control system it is. It could be a sociological system, it could be an economic system, it could be a biomedical system, or it could be your standard chemical system. Every control system will have these four components. You see a sensor that tells you what's going on. You will see a controller that is deciding what's going on the basis of the set point and the current measurement. Then you will see the actuator that carries out what the controller is saying, and then you have the process itself. The fascinating thing about it is that at every level in biological systems, at every level, you will see all of these four components. And therefore, if somebody is ill, if somebody is sick, really it makes sense that the first thing you're going to ask is what control system is responsible for maintaining whatever has gone wrong, and then what aspect of this control system is wrong so that we can fix it. Unfortunately, or fortunately, I don't know, medical students aren't trained that way. That's not the way they're trained. They're trained to understand this is what's going on with the system. When this happens, you do this, you do that, you do the other thing. But now people are starting to recognize that it is important to be able to understand that systems occur, and when failures occur in a system, you need to identify which component of that system. And many people in the medical schools are starting to recognize that we are, in fact, complicated systems put together. So next slide, please. So I don't need to tell the people in this audience what an engineering feedback control system is. And as I just explained to you, the room I'm sitting in, you have a sensor, you have a controller, you have an actuator, and you have a process. What I want to say, though, is please pay attention to this diagram because you're going to see it again. You're going to see it again in a completely different context. And I hope that at that point, you remember what I've shown you here. And it's going to be central to how I think all of us who work in the process systems engineering domain are going to be able to make contributions to being able to get precision medicine going. So next slide, please. And the next few slides are just going to be examples of the structure of biological system feedback. So you can see you have a control system. The sensors tend to be receptors, but not all. Then there's a control center somewhere, either in the brain or within the cell itself, and then there's an effector. Again, those four components you will see. Some specific examples, you will see it in the next slide, where we talk about the very first work that we did. The next slide, yes. This is the very first work that we ever did, going back to 1991, in trying to map out the Bioreceptor Reflex, which is the system for doing short-term blood pressure control. Believe it or not, we've been working on this for, not quite 30 years, 20 plus years, and we're still working on it. We're still trying to understand what's going on in the brain. So you see the bioreceptor neurons are these stretch-sensitive neurons that sense arterial blood pressure. That information is sent to the cardiovascular center, specifically a place called the nucleus tractus solitarius, NTS, where all kinds of magic takes place. And we're still just slowly trying to understand how the computations are made, but computations are made there. And this is where things differ from what we are used to in engineering. The information breaks out into two parallel systems, the sympathetic system and the parasympathetic activity, which then work on the arterial, and the other ones work on the heart, and so on and so forth. But if you just step back a bit, you will see that, again, you have your sensor, you have your controller, you have the actuators, and then you have the process that you're trying to control. The next slide is the one that you are all very familiar with, and well, most people anyway. And this is the blood glucose control, where you have your sensor, which is actually part of a functioning pancreas, and then your controller, where you make the insulin, and that is sent to the liver, where it does a lot of the reaction, where insulin works on glucose, and then it's able to control the glucose in the body. It turns out, ladies and gentlemen, this is the perfect example to demonstrate that when you want to treat a disease, you need to ask what part of the control system is faulty. So, for example, if the problem is that your pancreas is not making insulin, okay? So then that part of your system is what is wrong. You have a type 1 diabetes, and it doesn't make any sense to try and do anything else for you, but to figure out a way for you to put in insulin when you need it, okay? But now one of my very first postdoc ever, Frank Doyle, and his group have made significant steps in developing the artificial pancreas, which essentially replaces this controller with an MPC, motor predictive controller, and an insulin pump, okay? But it is also possible that the gain of your process is what is not as high as it should be. It's called insulin resistance. You're making insulin, but your system is not able to use it as well. You make a step change in insulin that is supposed to bring your blood glucose down by a certain amount, but it brings it down very little. The gain is not as high as it's supposed to be. Well, that is type 2 diabetes, okay? So the problem with type 1 diabetes is a controller failure plus actuator failure. But for type 2 diabetes, it's a problem with the process. And so for people with type 2 diabetes, what they need to do is to resensitize your system and things of that nature. So this is a perfect example. So if you go to the next slide, it shows a flow sheet of the calcium regulation. And unfortunately, I wish I had time to be able to discuss this much, but I don't. And so unfortunately, all I can do is show you that this is a case where you have several of these systems working together to control one thing, just one thing, calcium. And what do you find? You have the digestive system working with the cardiovascular system. So you see the pump, the heart, and all the circulating blood. Then you see the musculoskeletal system, that's the bone, and then you see the endocrine system, and then you see the urinary system. All of these are working together to do what? Just one thing: control calcium. And unfortunately, I don't have the time to go through this, but this is a fairly accurate flow sheet, process flow sheet of how your calcium is regulated. So if you go to the next slide, we'll see a control system type block diagram. And again, I'm not going to spend too much time on this. The good news is, if you go to the next slide, the good news is that this paper has been published. Yeah, you could scroll to the next item as well. This paper has been published in the Journal of Clinical Endocrinology and Metabolism. And the only thing I will say about this, and not dwell too much about it, is that if you want to see drama as an engineer, go publish in a Journal of Endocrinology or a Journal of Clinical anything. Okay, when engineers go to publish in a journal of clinical practice, you will run into the language barrier. And I'm not going to say a lot. You can find the paper and you can look at it, but we had to rewrite the paper completely from the very beginning, because the first time we wrote the paper, it appeared after the review that we wrote the paper in Russian, and the reviewer was speaking Portuguese, and then the editor was speaking Arabic. I mean, it was like nobody understood what anybody was saying. And I told the grad student, who was getting very discouraged at the point, I said, no, it is not their responsibility. We're the ones going into their house, okay? And so if I'm going to go to your house, I need to learn to respect the way you arrange your furniture, and I need to understand how to do all of those things. So if you read through the paper, you will now see that the paper was not written for Ajimiro, was not written for Mauricio, or any of you who understand control. It was written for people who are in clinical practice. So if you go to the next slide, then we would and then go next to the next one. I'm going to talk about, so if you keep scrolling, one more, stop right there. All right, stop right there. So I would like to, since I know Ajimiro is in the audience, I'm going to pick on him. I want to imagine one day in the not so distant future, Ajimiro wakes up in the morning and his Alexa says, "Bom dia, Ajimiro," and speaks in Portuguese. My Portuguese is not very good. In fact, not good at all. So I would switch back to English, and says, "Good morning, Ajimiro. Your doctor," and I'm going to call your doctor instead of Mary Foster. I'm going to say Dr. Julia, and Dr. Julia says that you should include a banana with your breakfast this morning because your potassium level is a bit low. And then says, "Oh, and by the way, you should spend at least 25 minutes on the stationary bike today because you haven't exercised in a while." All of this information, notice what I've just said. Ajimiro wakes up in the morning, and before anything happens, Alexa comes up and says something to him based on data, based on information that his doctor has said. All of this is made possible by a biointegrated sensor that can continuously monitor your body chemistry. All right, this is not too far-fetched, right? Okay, so next, Ajimiro, just go to the next one. And sophisticated medical data analytics, and the next one. And, well, imagine no more. Why? Because this sensor already exists, ladies and gentlemen. I have seen it. Okay, smaller than a grain of rice. It's been available since January 2016. Okay, and one of the alumni at the University of Delaware developed it, and I've seen it. And it's a tiny, tiny little thing, and they embed it just by your wrist, under your wrist, and it takes your entire blood chemistry, analyzes it, and sends the information wirelessly. Now, this should not surprise anybody. I don't know how many of you today are wearing a device, a watch, a Fitbit, or an Apple Watch, or one of those devices. It is measuring your blood pressure. It is measuring all kinds of things, and it's sending it wirelessly to your cell phone. And if you give access to your medical practitioner All of that information is available. So what I'm saying now, ladies and gentlemen, is not too far-fetched. The only thing that's missing right now is the massive data analysis that is going to make this happen. So if you go to the next slide, then you will see, I just scroll through everything. The definition, oops, go back please. Yeah, the definition of precision medicine, first of all, I would like to say that precision is not really what the people who named this, the students who've taken my statistics course understand the difference between precision and accuracy. You can be very precise and be wrong. So what they really mean is personalized medicine. But I've learned my lesson. I'm not going to go into the medical field and try to tell them how to run their show. So I would just call it individualized medicine or personalized medicine. If they want to call it precision medicine, they should go ahead. But this is an approach for doing more than just treatment, for doing disease prevention. And the idea is encaptured in what I just said earlier to Ajimiro. Ajimiro's potassium is not out of range yet, but it has been trending low. And so before he gets out of range, I want to do something before it's too far. And the idea then is to optimize health. If you're healthy, I want to keep you as healthy for as long as possible. And if you happen to get ill, I want to restore you to your set point or within the range as quickly as possible. And yes, I'm deliberately using control language because that is exactly what people in the medical field are doing. They just did not know that what they were doing was practicing control, and I will show you that that's the case in a minute. So if you go to the next slide, you will see some of the 4 principles that were put forward by Professor David Val. Next slide, please, Ajimiro. All right, so Mauricio, so this is what I've just shared with everybody. And again, I apologize for the technical difficulties. So then if you go to the next slide, this one, I'm going to need you to do it one by one. So wait right here, one by one. So what happens when you have a disease? Something caused that disease. So next hit, Mauricio. All right, so then there's a disease indicator. And then the first thing that you're going to do when you go to your doctor is they're going to do a diagnostic test. They want to find out what's wrong with you, okay? And so next hit, Mauricio. All right, so the test results come back. And the doctor is going to take a look at the test results. And next hit, please. No, you're going backwards. Yeah, forward. All right, right there. So there's going to be a desired target value. They're going to compare your test result to. So for the sake of argument, let's say it's your blood glucose. And they take your fasting blood glucose, and the number comes back, and it's 150. Well, we know that it's supposed to be below 100, and right away, your physician or healthcare person says, oh my God. So next hit, please. Is it diagnosis and it says you have diabetes. Now, we don't know if it's type 1 or type 2, but you have diabetes, okay? And then the next one. So now you come up with a treatment plan, and then they look at all of these things. Ladies and gentlemen, this is the diagram I was asking you to remember. I don't have to explain this to any of you in this audience at all, because now you can see exactly what's going on. This is the way people are being treated even today, ladies and gentlemen. Something happens, they order a blood test or something, they compare it with a set point, the physician or healthcare professional looks at it and makes a diagnosis, does a prescription, but it's not going to help you unless you actually follow the treatment plan, and that's like the actuator. So ladies and gentlemen, what does this tell me? This tells me that we can take the engineering feedback control formulation and use it to figure out how to implement personalized medicine. What do I mean by that? Think about the diagnostic tests. Right now, the big problem is I have to get up, go physically to a lab, they have to prick my finger, or they have to draw blood from my veins and do the analysis, and it takes about 3 days, and then all of that, the physician gets something done, and then there's a treatment plan. Imagine the day, ladies and gentlemen, where we will be able to have embedded sensors that are constantly measuring all of, like, right. So now all that information is available. I don't have to wait every 6 months. That information is made available, but it's too much information, ladies and gentlemen. Just a wide amount of information. Every minute, every day, every time. All right, so all of that information, human beings are not very good at staring at numbers. It doesn't tell us much, but computers are very good at that, and we can develop schemes that will help physicians make sense. Principal components analysis, machine learning, all of those kinds of things, including physiological models that will help people understand what's going on. And then how do you prescribe? Well, it is running those models in reverse, right? He says, if this is what you get, right? If your blood glucose is this, and this is that, and that is that, and all of that, this is what you have. You can run it in reverse. If I want this to happen, what do I need to do that I can manipulate? That's control. We know how to do that. You come up with the treatment plan, even how to implement this. Engineers can participate in this. So this, I would leave it this way. If you look into the paper, the INEC paper, you will see all the details about how people that do process systems engineering can get involved in doing these kinds of things, including understanding the physiology and the biology that is behind all of these things. So if you go to the next slide, please, Mauricio. Yeah, just scroll through all of that. Yeah, scroll through all of that to the next one. All right, so what I'm going to do now, and just scroll to the next one, is to talk about a clinical example. All right, and the clinical example, this is a real person that we worked with, a real hematologist and a real nurse. Okay, and I'm going to give you the results. And again, the good news is the paper has been published. So for us to understand this, and I have to ask Mauricio, how much time do I have left?
You shouldn't worry about that, because we have about 40 minutes if we go up to 15 in the afternoon. So we can make the questions and comments section, you see, so that we can listen to you. Please do not worry, okay?
Okay. All right. Well, thank you very much, because of all the issues that we've had. I just don't want to waste too much of your time. So for us to understand what I'm about to say, I need to give you some understanding of hemostasis. This is hemostasis, not homeostasis. Hemo as in blood, okay? Hemostasis. So what is hemostasis? If you were to cut yourself right now, if you're in the kitchen and you're not paying attention and you just nick yourself, you don't bleed to death. Why don't you bleed to death? Because of these two regulatory mechanisms: platelet aggregation and blood coagulation. One of them is the primary hemostasis that just achieves partial blockage with a platelet plug, but the platelet plug is not enough to stop the bleeding. Then the secondary process kicks in. It's called coagulation, where you actually get a polymer mesh that comes and sets the platelet plug in place. I will show you the control system in a minute, but here are the pathologies. One of them is hemophilia, excessive bleeding, where this system is not working as well as it's supposed to work. Okay, because it's not working as well as it should work, you don't stop the bleeding very quickly, and then you bleed more than you need to bleed. The other extreme is thrombophilia, where you are a little too aggressive. The blood clotting system is a little too aggressive, so the slightest nick you get in your blood vessel, it clots the blood, and that could cause heart attacks or strokes and things like that. You want to avoid both of them. And how do you do that? Next slide, please. This is the control system. And again, I apologize that I would love to be able to go through all of the details, but I can't. It's just in the interest of time. But you will see those 4 blocks again. You will see the sensor block, you will see the controller block, you see the actuator block, and you see the process block. Now, things are a little more complicated once you open up the blocks and look.
Oh, Deus.
What happens. Inside of every blood vessel, the blood that's flowing has red blood vessels, white blood vessels, and things like that, but then it has tiny little fragments called platelets. These platelets are very, very important. In fact, not just very important, they are central to blood clotting. So what happens? Platelets are moving right along in your bloodstream, and they're happy. If everything is fine, they're happy. If they run across collagen, ladies and gentlemen, as the Americans will say, all hell breaks loose. Why? Because anytime you see collagen in your bloodstream, it means that there has been a breach of your artery wall or your blood vessel wall. Once that happens, it releases collagen, it exposes collagen to the blood, and the platelets come and they bind to collagen. To make this simple, let's imagine that the first platelet arrives on site, binds to the platelets. The first thing it does is it degranulates. What does degranulate mean? It means that it releases thromboxane A2, releases ADP. And what are those things? They're chemoattractants. What's a chemoattractant? A chemoattractant is something that literally holds a microphone to his voice and says, everybody that is within the hearing of my voice, come over here. I have something to show you. Okay, so all the platelets that are within thromboxane A2 and ADP are attracted to that site. Once they come to that site, they do the same thing of degranulating and bringing more platelets out. So I want you to imagine the first platelet gets there, brings in three platelets, and each one of them brings 3 more platelets. And you can see it that the platelet size will grow 3 to power k, where k is the number of times that they've come around. And you can see that this would ordinarily be open loop unstable, but there are other kinds of things to stabilize it. But that's the first one. You want the platelets to come very, very quickly and to bind and to stop the flow. But then the secondary one is the coagulation, where a series of reactions takes place. And pay attention to these, they take place on the platelets. All right, so as the platelets are accumulating, the reactions start to take place. And these reactions is a series of them. Think about the first reaction to the next one, to the next one. It's a cascade, but the second to the last reaction catalyzes the first reaction. So I hope you are getting this image. Reaction 1 to reaction 2 cascades down to reaction 3, and reaction 3 catalyzes reaction 1. All right, so that goes very quickly, but reaction 4 is where you make fibrin, and then you make fibrinogen to cover that shiny red thing you see on your wound. That's fibrinogen. So that's how this works. And I wish I could tell you a little bit more. There's like another several minutes that we could spend, but that's enough. What I'd like to leave you with now is to ask a simple question. It's a rhetorical question, but a simple question none the same. Can you imagine what will happen to somebody who doesn't have platelets? Let that sink in for a second. If you don't have platelets, you'll bleed to death. That's it. There is no, the means by which this control system works is through platelets. If you don't have platelets, you die, bleed to death. The good news is there's not a human being alive anyway who doesn't have platelets, but there are people who have fewer platelets than they should have. So if you go to the next slide, please. So the disease is called, and you can just scroll through it. The disease is called immune thrombocytopenic purpura, okay, ITP. And so if you scroll through, Mauricio, please. All right, so this is your platelet count should be somewhere between 150 billion cells per liter and 400 billion cells per liter. If you're within that range, you're normal. If you're between 30 and 150, you may not even be symptomatic. You're fine. You can still continue to function. If you are below 30, you have a high risk of bleeding. And ladies and gentlemen, if your platelet count is below 10, you will be strapped to a bed. You cannot be allowed to go out because if your leg against something, you could bleed to death. So next slide, please. So the characteristics of ITP is, so what was the personalized approach we used? We decided we're going to do mathematical modeling, okay? We're going to develop and validate a custom-made pharmacodynamic model for this particular patient, collect data, and analyze it for insight. And this is what we do in our group. We develop models, we collect data, we validate the models, we analyze the model, and then we use it to make decisions, okay? So the candidate control schemes that we're going to investigate, I'm going to show you some quick results, fixed dose, open loop, that's the current practice. And then we're going to look at optimally tuned PI controller and a variable dose optimal open loop control. All right, next slide, please. All right, so this is the good news, like I said, is that this paper has been published, and it's been published in the Journal of Process Control. In this particular case, it was important because my audience are people like you to see how we can use control to solve a problem like this. And therefore, I didn't have as much drama involved in this because the people who were reviewing the paper understood the control that I was talking about. And even the biology that they didn't understand, it was just, explaining what ITP was, explaining how all of these things work. So this paper was published way back in 2016. So feel free to go to Journal of Process Control and seek it out, and you will be able to fill all gaps of things that I will not be able to fill in here. All right, so next slide, please. The next slide shows you how we developed the model and the data. So what you're looking at here, the top spikes that you see are the doses, the days that the patient went to the doctor and the doses that he got, it's a he. And the red dots you see are the actual data, platelet count for this patient at the various times. The green ones are the data that we used for validation. The red ones we used to fit the model. And the blue lines that you see are the model predictions. And for those of you who may not be familiar with modeling biological systems and you see this kind of deviation, and you can say, oh, this is not a very good model. It actually turns out this is a very, very good model. It was the physician was absolutely surprised that we could capture this much because the patient was also undergoing steroid treatment for all kinds of other things, but that we were able to match it this way. In the interest of time, the only thing I want to point out to you is if you look at this table, I have highlighted this TPLT parameter. That is the platelet lifetime. And if you look at that, the platelet lifetime for healthy subjects is about 10 days, 253 hours. So all of you who are normal healthy subjects, you turn over your platelets about every 10 days, okay? And the reasons for that, I don't have time to go into it, but just it's enough to say that this is central to being able to maintain the integrity of your hemostatic system. So every 10 days, they turn over. But for this patient, his platelet lifetime is 113 hours, okay? Not even half of what it is for normal people. So here we are, a patient that doesn't make enough platelets in the first instance, and then the one he makes don't even last as long, all right? So next slide, please. We're gonna run through some of the results very quickly. I wish I had time to go through this, but this is a model analysis. This is called a dose response curve. What does that say? If I give this patient an injection of romiplastin, how does the platelet count respond? I need you to look at the red dash line. That's what happens when you start with 5, platelet count of 5. You can see it go up, peak, and then come back down. Notice how much time it takes for it to go up and come back down. It's about 28 days. All right, so next slide, please. So these are simulations. We didn't do anything with the patient. We just took the mathematical model and we said, what happens if we use a fixed dose, open loop? You show up every 2 weeks or you show up every week and we give you this dose, 2 microgram per kilogram or 1 microgram per kilogram or half a microgram per kilogram, okay? And you can see weekly is up above, biweekly is below. I don't really need to spend too much time on this, but take a look at it. It's oscillating. It is still oscillating. And the question is, why on earth is this still oscillating? This is open loop, ladies and gentlemen. It's not as if we're doing anything particularly interesting to this, okay? So that tells us something. All right, so next slide, please. So now we do an optimally tuned PI controller. What does that mean? It means the KP and the KI, if you're using MATLAB, or you can use KC and 1 over tau I, it's standard, it doesn't really matter. And the idea is we use F-min search, again on the model, with an initial condition and say, find me the best values for KP and KI when my delta T, my sampling time, is weekly or biweekly, and when my set point is 70. And you can see to the left that when you do a weekly treatment, you can in fact settle it down to 70 without oscillations. That's fantastic, all right, using optimally tuned PI controller. But that means we're measuring the platelet count, and on the basis of the measurement of the platelet count, we take control action. That's what we get here. But now look over to the right side. When we do biweekly, if you focus your attention only on the black dots, these are the measurements that we take. It looks as if we're doing well, but in fact, we're not. What happens in between samples, you see we are still oscillating. And ladies and gentlemen, this is the best optimally tuned PI controller. And this is simulation, ladies and gentlemen. So this tells us something else is going on. Something else is going on. And without going into, if you go to the next slide, I wouldn't spend too much time on that. But again, if we just do optimal control, forget about PI. This is a controller like we're using F-min search to find U of K that would get you get something on the left-hand side that is exactly like your optimally tuned PID controller. You look to the right side, you see oscillations again. So if your optimal controller is oscillating, it is telling us something fundamental. And so if you go to the next slide, and this is the punchline, ladies and gentlemen, here's the deal. For this particular patient, its natural response to a pulse of romiplastim takes 14 days from beginning to peak, and from peak to when it goes down, 14 days. So ladies and gentlemen, as long as you treat this particular patient every 2 weeks, you will never, ever get rid of the oscillations. Let me say that again so that you understand. This patient's natural response time to romiplastim is 2 weeks. That's a natural period of response. So as long as I treat this patient every 2 weeks, I will settle down to a limit cycle that is like this, and you can see it on the right-hand side, which is what the optimal controller showed us. As long as you're doing delta T is 2 weeks, that's what you're going to get. So what is the solution to this problem, ladies and gentlemen? I wish I could tell you that we could have done something fantastic like using NPC and all of this. No, the solution is simple. Cut the dose in half and treat every week. Why is that important? Because it solved the problem, first of all. It broke us away from treating this patient at his natural response time. But it also pointed out to the hematologist that when this drug was developed, it was developed, clinical tested, and for the vast majority of patients, 95, 98% of them, 2 weeks is the time to use to treat them. That wasn't their natural response time. And by treating them every 2 weeks, they could treat them very well, and 98% were treated well. Well, this particular patient happened to be one of the 2% that needed a different delta T. All right, so the insight that we were able to gain by using control and things like that, is that for this particular patient, we were missing the fact that he was different. Okay, so next slide, please, and then we'll round up. All right, so the key finding is the pharmacokinetics of romiplostim for this specific patient was just different. And so we were able to customize the treatment for the patient. And then maybe I should mention this, okay? In discussing with all the people we were working with, can we explore continuous control with a patch and things like that? They were a little bit reluctant because, yes, we're dealing with human beings, okay? That is the challenge we're going to face. As long as we work with people in the medical field, and as long as they're going to be treating human beings, we have to be very careful. So let me summarize and conclude. Please, let's go to the next slides. And again, I apologize for having gone for so long. So personalized medicine is going to be the way of the future. There's no question about that. But much work needs to be done for us to realize this promise. We need the development of novel technologies and methodologies. And I believe, and I hope I've convinced you, that the engineering perspective is a potentially viable vehicle for achieving these goals. And yeah, I see somebody has a question. Let me get to my last slide, and then I will take the question. So just scroll to the next one. Just scroll all the way through.
Oh, sorry.
Yeah, no, that's fine. So medical schools are actually working with interested engineers. I work with people at Thomas Jefferson Medical School all the time. And our biomedical engineering departments are working with medical schools. And so I also think that engineering schools should be incorporating principles and methods of biological control systems into the graduate curriculum in control engineering and in systems biology. And in fact, I just finished teaching the the students just turned in my exam today, and the first problem I gave them was an application of control theory to a biology problem. So let me scroll then to the next few slides and just round up, and I will take that quick question. So here's the acknowledgement of the people who have worked with me. On the left side, former and current students. Mark Whistle, actually, when he got his PhD in 2009, did a postdoc and then went to work at Mount Sinai Medical School in New York. And now he's back at Clemson as a professor at Clemson. Chae-Hung Tsai is the one who did virtually all of the work on the hemostasis that I talked to you about. And if you look on the right-hand side, you will see my collaborators in medical school, Jan Hook, Boris Holudenko, Ulhas Naik, Jim Schwaber, and Raj Vadikepali. I still work with those guys till today. We continue to work. So next slide is the final. Yeah, that's the usual people that give us money. Next slide, please. Next slide. Yep, and one more. There is Chae-Hung. Oh, please go back. There's Chae-Hung Tsai. And the reason I went back to spring 2012 is because this is where the last picture I have of Chae-Hung Tsai. So again, thank you very much. I will stop here, and I want to apologize again for all the technical difficulties we had. And I hope that we will be able to. I'll take some questions now. Somebody had a question before that flashed by as I was finishing up. Please ask your question.
Okay. Thank you very much for your presentation. We are sorry also for the technical problems that we had, but thank you. I think the presentation was very good and important for us, very important, because I think that everybody in the audience loves control.
Yes.
It's so good to see that we can apply all concepts from modeling and validation of models and simulation and control to medicine. So it opens quite a new perspective, and it is also very important for Brazil. So I want to ask people that want to make questions, please make your inscription in the chat so that I can call you, okay? Just show your intention, put in your name. Yes, I have already one.
Okay.
Fabio Pereira is going to make a question. Please, Fabio.
Good afternoon. Can you hear me?
Yes, loud and clear.
Okay. Well, Professor OGUNNAIKE, did I say it right?
Oh, yeah, OGUNNAIKE. Yep.
Okay. Thank you for your presentation. It was very nice for me. It's good to me, not in a on professional point of view, but it's also in a personal point of view. So it's good to hear a Black person presenting in the university. You know, for me, it's very important to see you. Well, basically, well, I'm an assistant professor here in Brazil, in Fernando de Rio de Janeiro, and my question is a very complicated question because, well, I know that biological systems have a large range of scales, time and space.
Yes.
Okay, so it's very hard to simulate and to predict all these scales.
Yes.
Okay, it needs intensive computational resource, and it's not for everyone to do this kind of simulations on all scales. And how do you deal with this in your models? And how can you produce real-time tailor-made medicine since you have these large scales in this time in biological systems? And what do you think about this wave of new data-driven models like reinforcement learning, machine learning, how it can help in your applications? And at the same time, I have seen that you have the data and then generate the model, and then you don't have physical constraints or biological constraints inside these kind of models that you generate by data. So could you comment this for me?
Absolutely. Very, very good question. So the first thing is, how do we handle all the complexity in these biological systems? It's like everything else. If you notice, the kinds of systems we deal with in chemical processing are also complex. Maybe not as complex as biology, but they're complex nonetheless. So when you're looking at a refinery, you see all kinds of things, but you need to do the entire thing. You can take, it really boils down to which are the most important aspects of your process. And you select those and you do the best that you can with all the information that you have. The example I'd like to use is, if you want to come to my house in Delaware and you fly to the Philadelphia airport, if I give you a detailed topographical map that has all the details in it and you're the only driver, you will get lost. Okay? Not because the information is not there, but you don't have the right amount of information. On the other hand, if I give you what Americans call a stick map that just draws sticks that are not to scale, that says if you get to I-95, go south. If you get to this 141, go north. When you get to 48, take west. When you do this, when you do that, when you do all of those things, you get to my house. Why? Because I have put in the precise information you need to answer the question. So one of the challenges we face when we're dealing with modeling biological control systems is to ask, what do we want to use the model for? And then put in the amount of information, the correct amount of information, the right amount of information. We start out by not putting too much, and then we only add as we need. So that's the first part. The second part of your question is also a very, very important one. How do we use all this data? Data is important, and data we need to use as much as possible. But I will warn you, data is just data. And I will make a statement in English, which I hope is very clear. Whatever information is not contained in your data is not going to magically show up in your analysis. I don't care how good your analytical tool is, if the information is not there, it is not going to find it. What do I mean? Your information is only as good as the data, all right? And so I've heard people foolishly, I must confess, say that with all this data that we have and machine learning and everything, this is the end of physics. This is the end of biology. This is the end of any of that, because we don't need, that is absolute foolishness. Because the only way to prevent us from going over the deep end, prevent us from getting into trouble, is to lay our foundation on material and energy balances, on laws of physics. So the best way is to combine them, not to throw one away for the other. I hope that answers your question.
Did you answer my question? Thank you very much. I'm very,
okay.
very glad.
Good.
Yes. We have another question from Professor Triweiler.
Oh, yes.
Make a question.
My old friend, how are you?
I'm fine, thank you.
Yes.
Thank you very much for your excellent talk.
Oh, thank you so much.
Really amazing your talk.
Thank you.
Including it to give me the desire to understand more this area.
Yes.
And
Yes,
I would
yes.
like to know if you can explain us a little more about models.
Yes.
What kind of models we can develop? Usually we use phenomenological models and so on.
Yes.
But
yes.
we need to combine these models with the new kind of systems. Maybe you can give us some reference, some good tips to start, and so that we can include in our undergraduate classes.
Yes.
And it was really amazing, your talk.
Thank you very much. And I'm happy to send you some material afterwards. So if you send me email, I'll send you some material. But what I'd like to say is, let's start simple. I'll give you an example. People are talking about vaccines right now. One of the things that I gave to my students in this year is a simple 3-state model of the immune system. Now, everybody knows the immune system is horrendously complex, but it is actually possible to use 3 states to capture a significant amount of what goes on with the immune system. And I give the students a chance to explore what happens when you put in a vaccine once, and you will see it. It's an inverse response system. You will get worse before you get better. And if you actually do the analysis, you will see the right half plane 0. Okay, and then after a few, give another shot of the pathogen. You see that your system doesn't respond to it at all because it already has. So let's start simple, and then we can build on those. We can add more and add more as we need. So models of signal transduction pathways can be 4 or 5 states. Does that capture everything? No, but it captures enough to show the students what some of the dynamics are. Now, when you start talking about this patient that I just told you, the model we developed was about 19, 20 differential equations. But we didn't start out saying that we're going to put in 20 differential equations. We started adding more, and then we collected data. And there are cases where your model has gone as far as it can. Then if you compare it to data, you will see differences, and then you can use data analysis to capture what you have not been able to capture. In other words, you've used your basic biology, basic physics, basic chemistry, basic material balances to capture what you can. And then the residuals, you use data to capture them, and then you combine them. There's no technical method for doing this, but like all engineers, you use judgment, and there's an art form to this, like most of the models that you've been developing all along. So
thank you very much. Start simple and grow up.
Yes.
Thank you.
Thank you.
Yes.
Maybe we are all waiting for another book like your own book that we have been using for a long time, now including the models for these systems. That would be very nice.
In fact, if you want, I'm actually right now revising the book, and I have a new chapter, chapter 14, which is on biological control systems. I will be happy to send you the first draft of that, and so I have your email, Mauricio. I will send it to you, and then Ajimiro and my friend Triweiler, I will send all this to you, and I hope one of these days COVID will allow us to be able to see one another face to face again, and I will be happy to come and visit you, and maybe go to a stadium to watch a football game with you.
Oh, sure. We have 2 more questions.
Okay.
Two people have already made inscriptions. Professor Tavares spent some time in Delaware. I don't know if you have met there. I will pass the word to Professor
Yeah.
Frederico Tavares.
Yeah.
Hi, my name is Fred.
Yeah.
I saw that. Thank you, first of all. Thank you for the class. It's more than a talk. I have a very exciting perspective.
Yes.
But let I ask you. I saw that one of your publication you published with Professor Stanley Sandler.
Yes.
I spent some time with him.
Yes.
If I understood, in your model, you include non-equilibrium thermodynamics or something like that?
we started out using some of that, and that was why we worked with him, because like I was explaining earlier, you start simple, and if you're unable to explain some of the things that are going on, you start making them more and more complex, because when the way the drug is distributed in the body, there's some equilibrium that are going on, and so we got him to help us understand some of the dynamic of the drug distribution, especially when you have these kinds of mixtures, and as you know, is very brilliant in doing that. So yeah, we included some of that information. Yes.
Interesting. But my question is, in the perspective for a student from doctor from medicine,
yes,
they are afraid about this huge increase of data banks,
yes,
and machine learning and all the huge data that people collected, and now they are put together in a machine learning, something like that. And
yes,
maybe is doing better diagnose than they can do. So,
yes,
so in this not engineer perspective, but in
yes,
students that are finished the medicine, what do you think about going to happen with these guys?
Well, so I think it is rightly so that people are concerned about data for all kinds of reasons. Some of it security and things like that. But this is the wave of the future, where I mean, Google has data on every single one of us. Amazon has data on every single one of us. That ship left the port, if you understand the English. And so it is to help people in the medical field to understand that, yes, everything is a two-edged sword. It can be used for good, it can be used for evil. And that, so if we concentrate on using it for good and doing the best that we can to prevent it from being used for evil, we will get the benefit as opposed to the others. The other side of the story is there are now many more engineers that are medical doctors. Believe it or not, the medical schools in the US are recruiting a lot of engineers. You get a first degree in engineering and you go to medical school. And so they are far more comfortable with the kinds of things that we're talking about. And so it's slow, but we will continue to make progress.
Very interesting. Thank you.
Yes.
Thank you. Argimiro has some questions too.
Yes,
Yeah.
Argimiro.
Yes. First, I have to thank you, Tunde, for accepting our invitation for this last seminar of the year of the LADES-GIMSCOP collaboration. That's very glad for us in this wonderful talk you have done. And thank you very much for that. And nice to see you again here with us.
Good to see you. Yes.
But remotely, but
Yes.
at this moment.
Yes.
Okay. One of the questions I was make was regarding to the model, but some you have talked about that to George questions, but you have told us that the model for the platelet count control, you have used a very large model. It's about 1900, 1920, I think. This was the size, very huge size, I think. Yeah. And as you said, you have to keep as simple as possible, because you have done some work together here. It's together with us, the Professor Eloisa Sanchez. I think she's still here. Yeah, she's still here. That's good. you have a student that was working with the cardiovascular system, and you have to do the drug delivery and so on. And they also start these very simple models with, I think, about 100 states. And it was quite nice to reproduce all this oscillation, oscillatory behavior that you have the cardiovascular system. But, you know, it's a very small piece of the human body. And you put this in interaction with all the other utilities you have mentioned. Respiratory, urinary, digestive,
everything.
So on. It's a big plant-wide control. What's your comment about if you can go further and do this kind of control? What do you suggest for that?
Yes.
Okay. And the other question I have to do is regarding to the ethics for when you have to collect data. You have some problem with that?
Yes. So let's answer the first question first. You would notice that when we do plant-wide control in engineering, we don't use CFD, all right? We don't use CFD models. We don't use molecular simulation models for plant-wide control. So it's the same thing with the human body. It would be foolish of me to use very detailed model of every cell and things like that and try to put everything together for plant-wide control. You need to use the control that is applicable, the model that is applicable for the kind of control you're trying to do. So when I send you this chapter 14, you will see one example in which we're looking at balance keeping in human beings. If you look at the mathematical model, it's relatively simple. It's about 3 states, okay? Now, there's a lot going on if we wanted to model how the muscles move and all of that stuff. Simplify down and you check it against the physics that you know. In this particular case, if you linearize around a certain steady state, and then you look at the poles, lo and behold, you will see a right half plane pole, which tells you the system is open loop unstable, which, you know, just like when I said with the vaccination case, you will see the right half plane 0 in that case. So it tells you that even though it's simple, it captures enough of the things that are going on. So you use the right kind of model. Now, if you want to deal with diabetes, okay, you're looking at the functioning of the pancreas. Now, there are a lot of other things going on, but you focus on that. It's like looking at the crystallizer in your, there are all kinds of things going on, but you focus on your crystallizer, and anything else that is coming will be treated like a disturbance, okay? So it really is a question of being creative in selecting your boundaries, and then once you selected the boundary of interest, selecting the appropriate type of model. The second half of your question is a much more difficult one. Ethics is a very, very difficult one. And I get asked that question every time, and the answer I give is, first of all, I am not an ethicist, and I don't pretend to be one, but there is no way we're going to make progress without having ethicists at the table when we're dealing with the kinds of things that we're dealing with, because there's so many issues, some that we haven't even thought about. I mean, we can do all the mathematical modeling and engineering and the medicine and bring in people like Professor Sandler to help with the thermodynamics and things like that. We do all of that, but we need the ethicists at the table to say, this is science, this is now ethics. And we're not philosophers, we're not ethicists, but we need them at the table. And we even need people with policy. So I just got a grant where we are working with people within the policy arena to help with how we're going to do intervention. This is on COVID-19 in the state of Delaware. How we're going to do intervention when there are people who believe that you shouldn't interfere with their lives and things of that nature. But you raise an absolutely important question, and I wish I had a better answer for you.
Yeah, but we have to deal with that too. And that's
Yes. Yes.
Thank you very much for your answers.
Obrigado.
Nada.
Oh, thank you. I have just one last question.
Yes.
Last week, we received a committee of international researchers that came to make an evaluation of our graduate program, School of Chemistry. We had Professor Grossman from
Oh
Carnegie
yes,
Mellon,
Ignacio. Yes.
yes, Ignacio, Brad Olsen from MIT.
Yes,
and
I know Brad. Yep.
yes, John Woodley from DTU. And
Okay.
the thing they asked us was, well, they said they liked our research lines, but they asked, what about your interactions regarding medicine?
Yeah.
They asked that, and we still do not have, and I think that's what we have in Brazil. It's what we don't have in Brazil. We really don't have, as far as I know, collaborations between chemical engineering departments and medicine groups. At least, you see, not general groups doing that. What is the, how is it in USA? Is it very different? The departments already are having this collaboration.
Oh yes. Oh yes.
Yes.
Oh yes. In fact, I don't know if one of my students is still in the audience. I just picked up a student this fall. She will be working with me and somebody in our medical school. And so I've had a sequence of students, about 5 or 6 of them, who worked with people in the medical school. So we have a very good connection with the medical school, and people at MIT have connections with Harvard Medical School. People at Carnegie Mellon have connections with the University of Pittsburgh Medical and things like that. And so many universities have these kinds of connections. The other thing that could help is if you had a biomedical engineering program. The biomedical engineering program is the perfect bridge between chemical engineering and the medical school.
Yes, we do have. Okay, so Tunde, I would like to thank you again. Thank you very much. Sorry for all the technical problems, but I think that I consider that this lecture had a profound impact in the audience, in our researchers from LADES, because as I said earlier, they love process control, and the fact that they can apply that for medicine is really very attractive. So thank you very much. I have one personal aspect. My daughter is graduating next year. She will be a doctor. She is studying medicine now. So in my family, we are trying to put these things together. It was very interesting also from this personal aspect. So thank you very much. We are very glad and honored to have you here. Thank you.
I'm very grateful to you, and I hope one of these days we'll be able to see you again. So obrigado and goodbye.